Okay, good morning. The point of today's notes is to solidify what we already know about work and the different types of energy. So the first thing we're going to do is we're going to break up everything we know about energy right now into a little flow chart. So we know that there are different types of energy. Okay, some of the types, and I'm going to kind of fill this in different places, so I'm going to jump around a little bit. The types of energy we know so far are kinetic energy, which is energy associated with something that is moving. We know about gravitational potential energy, which is energy that is associated with an object being above some surface, some massive object, such as the Earth. And we know about elastic potential energy, PES, and that is energy associated with the stretching or compressing of some object. Okay, so those are the three main types, and I've been telling you that these three main types are all referred to as different types of mechanical energy. Okay, and mechanical energy, they're all referred to as mechanical energy because you can transfer them back and forth from KE to PEG to PES and back very, very easily. Okay, it doesn't take too much. Well, it's not really what I mean. It's very easy. The transformations happen very quickly and easily. On the other hand, there is another type of energy that's not mechanical energy, it's still energy, called internal or thermal energy, and I like to keep that separate because once you have an object that has generated some internal energy, let's say that the kinetic energy for something sliding over a rough surface, friction acted on it, it took that kinetic energy away and it became internal energy, you can't take that internal energy back out and put it into kinetic or gravitational potential or spring potential, okay? At least not the way we're talking about it. So there's a real quick flow chart. And how do you get energy to convert between one type or the other? Well, that means work has to be done. Okay. So right now we're going to talk about what we like to call the work energy theorem. And the work energy theorem says something like this: if positive net work is done by an outside force the total energy of a system will increase. If positive net work is done by an outside force, the total energy of a system will increase. If negative net work is done, then the total energy of a system will decrease. Okay, so here's this statement written in equation form, and this is in your reference tables. You can go and look this up. Work is equal to delta E sub T. Work is equal to the change in the total energy, where the total energy, ET, is equal to kinetic energy plus both types of potential energy plus Q, which is internal energy. Okay? Now, here's an important thing that I think you should understand. When we talk about outside forces doing work, okay, this word right here, outside force, we don't mean any force. We mean the force outside the system. And it took me a really long time to realize this, but there are certain forces that are considered outside forces in this case. Your outside forces are things like the applied force, tension, and the normal force. That's it, really. The other forces that you know about, gravity, friction, and the spring force, surprisingly, they're already accounted for. These forces, if our system is set up right, these forces don't change the energy of the system. Applied forces, tension, and normal forces do. Let me show you why these forces don't change the energy of the system. If gravity acts on something, you might think, oh, well, that could be an outside force. No, think about it. If gravity is acting on something, that's going to change which type of energy? gravity is associated with gravitational potential energy. So that's already accounted for when we talk about the potential energy changing. If gravity acts on something, okay, if gravity acts on something, it changes the gravitational potential energy. That's already accounted for in the system. Same thing with friction. That's already being accounted for by Q. If friction acts on something, if our system is defined broadly enough, then that energy will turn into Q. And spring force, that's another type of potential energy. These three forces here, the applied force, tension, and the normal force, what they really go in to do, if your system is defined broadly enough, is change, let's say, the kinetic energy or increase the energy in the system. Okay, this is kind of tricky. I'm being honest, it took me a long time to figure out this right here. You have to define your system, okay, carefully in regards to where is the energy going, where is it coming from, where is it going to. All right, let's move on to some examples. So, in the examples, what we're going to be doing is we'll look at it. We're not going to calculate right away, but first thing we're going to do is determine, okay, what type of energy is being changed here. So, a 1,200 kilogram car moving at 8 meters per second has 2 times 10 to the 5th joules of work done on it. What is the car's new speed? So some work is being done on this car. What type of energy do you think changes? So the first thing we need to think about, we need to determine the type of energy that changes. In this case, what type of energy changes as the car has work done on it? Well, probably the kinetic energy. So KE. All right. So here's what that brings us to. The potential energy is not changing. The either gravitational or elastic potential energy, spring potential energy, and it doesn't say anything about friction necessarily. We don't have enough information on that. So when we say that work equals a change in total energy, really what we mean here is that the work is changing. Yes, it is changing the total energy. More specifically, it is changing the kinetic energy. So that means that the work done is equal to the final kinetic energy minus the initial kinetic energy. We could expand that equation out further by saying that the work done equals 1/2 mvf squared minus 1/2 mvi squared. And now we simply plug in our numbers and we go to solve for final velocity because we want to know what the car's new speed is. Well, all we've done is we've realized that the work changes the kinetic energy. We have expanded our equation out to account for the variables that we have. Now we're just going to solve for the final velocity. So I have 2 times 10 to the 5th joules equals 1/2. M is 1,200 kilograms. VF is what I'm looking for. There's a squared, don't forget that. 1/2, 1,200 kilograms, 8 meters per second squared. Now, if I do all this math, 2 times 10 to the 5th, I'm just going to write it over here, is 200,000, I believe. Yep, 200,000. Half of 1,200 is 600 VF squared. And 1/2 times 1,200 times 8 times 8 is 384 or 38,400. I'm going to add this to the other side. Divide by 600. And take the square root. And we get 19.93 meters per second. So work was done on the car. We said the kinetic energy should go up. And just as we said, the speed has increased because kinetic energy changed. We did work on the car to change the kinetic energy. Okay? So that's the relationship in this case between work and kinetic energy. Now in another case, like the one below this, it says 20 joules of work is done to lift a mass from the ground straight up to a height of 2.5 meters. What is the mass's final potential energy? Well, in this case, you're lifting something up. How is work changing the energy? Well, guess what? Work goes into the work that's done, changes the gravitational potential energy. PEG changes. Okay? The work that's done equals the final gravitational potential energy minus the initial gravitational potential energy. So, if that is the case, then let's think about this. The object, the mass, starts at the ground. If it starts at the ground, that means the initial gravitational potential energy should be 0. So look at this. That means the work that's done is equal to the final gravitational potential energy. Well, wait a sec. I know how much work is done. 20 joules is done of work. What is the mass's final potential energy? Look at that. We didn't even have to do anything. This is kind of like the question where back in the last unit where we talked about impulse. And when we talked about impulse, we said impulse is a change in momentum. If they told you the impulse, then they ask you for the change in momentum. You just, hey, wait, that's the same thing. Impulse equals change in momentum. In this case, we have something similar. We just need to realize that the work done in this case is equal to the change in gravitational potential energy. We know how much work is done, so we know how much it changes. If it started at 0, then the final is just equal to that change, 20 joules. Let's do one more example. How much work is done in order to give a spring with a spring constant of 900 newtons per meter and elastic potential energy of 76 joules? So what type of energy is being changed? In this case, we're stretching something out or compressing it. I guess it doesn't really say. But the elastic potential energy is what changes. So once again, we have work equals, of course, it's a change in total energy, but in this case, we're specifically changing one of the types of potential energy. Work is equal to the change in spring or elastic potential energy. And you'll see we have pretty much the same case as before. We weren't told it was stretched to begin with. We're just kind of assuming that it wasn't stretched to begin with. So there's no initial elastic potential energy. We are told that 76 joules of work was done. So guess what? The final elastic potential energy is 76 joules. Now, because we have the spring constant in this case, we could go back and figure out how far it's stretched, but that's not what the question asks. Just like in the last problem, we could have gone back and figured out what the let's see, we knew the height. We could have gone back and figured out what the mass was, but that wasn't what we were asked to do. We were just asked to find the final potential energy. All right, I think I'm going to stop there. I'm going to upload this, and then we'll come back and I'll do the back part with you guys. All right, I'll see you in a bit.